What's happening to Polaris, the world's most famous star? Have you ever seen those stunning long exposure photographs that capture the rotation of stars near the celestial North Pole? At the heart of that swirling motion created by the celestial sphere's movement lies the most famous of all stars, the North Star, or Polaris, as it has been known in Latin since the 18th century. Polaris is a mere 42 arcminutes away from the celestial North Pole, which is almost 1.5 times the diameter of the full moon. This might seem significant, but when compared to the vast expanse of the entire sky, it's practically nothing. As a result, Polaris, unlike the stars further from the pole, which trace increasingly larger arcs, appears nearly stationary, even in long exposure photographs. Stars very close to this imaginary point of rotation seem not to participate in the apparent rotation of the sky. And it's precisely because of this unique characteristic that Polaris has become the symbol of the cardinal point par excellence, the direction north. In our hemisphere, it has represented one of the earliest ways humans adapted to their natural environment, orientation. But has it always been this way? Absolutely not, as we're about to discover. But wait a moment. The current North Star isn't just an icon of our sky. It's also, and more importantly, a real astronomical object, still full of mysteries. Star of Navigators, North Star, Polaris, or simply the Pole Star. There are many names we give to this star, which is undoubtedly one of the most important in the entire celestial sphere. Polaris has been known for tens of thousands of years, yet until recently it kept some secrets hidden from us, revealed only through the most sophisticated astronomical techniques. Strange for a star that always seems stationary and visible, as if it's always ready and available to be examined in every possible way, don't you think? By the way, finding Polaris is very simple. Look for the 7 bright stars of the Big Dipper, then start from the 2 stars opposite the handle, which are called Merak and Dubhe. From there, connect them with your gaze and extend that distance about 5 times. You'll find yourself right near Polaris. You really can't miss it. If the sky is dark enough, around Polaris you'll see other stars that form the other dipper in the sky, the Little Dipper. This asterism coincides with the constellation Ursa Minor, of which Polaris is the brightest star. So much so that on maps it is often referred to as Alpha Ursae Minoris. But let's debunk a myth right away. Polaris is neither the brightest nor the largest star in the sky. There are in fact at least 48 stars brighter, so much so that often due to light pollution, it may not even be visible from large cities. When we talk about the great luminosity of Polaris, we actually refer to a more symbolic luminosity, because like a beacon in the night, this star always in any way points us north. In fact, Polaris is called so because it is located at a very important point in the sky called the celestial North Pole. Here's how it works. The Earth rotates around its axis, which is tilted by 23.5 degrees, relative to the perpendicular direction of its orbital plane. And this axis points to 2 points in the sky, namely the celestial North Pole and the celestial South Pole. Because of this, throughout the night the whole sky seems to rotate around it, while it, being at the center of rotation, appears stationary. Therefore, the further north you are, the higher you will find it in the sky. If you ever get the chance to cross the Arctic ice to the geographic North Pole, by looking up you'll find it directly overhead in the point of the celestial sphere called the Zenith. To be precise, the star is not exactly at the pole. It is very close, about 0.7 degrees away, which is just slightly more than the angular size of the full moon. By taking long exposure photographs known as star trails, we can easily see this. Polaris traces a tiny circle around the celestial North Pole, but it is not exactly at that point. But the story doesn't end here. There's another fact. Polaris only started being called by this name in the Middle Ages, when having reached 3 degrees from the pole, people began to realize its importance for navigation and orientation in general. Hold on a second. Does this mean that Polaris changes its position relative to the pole over the centuries? How is it possible for the North Star to move over time? Well, No, actually, the star remains stationary. What changes is the position of the celestial North Pole as a result of the Earth's millennial motions. Often when we think about the movements of our planet, we consider only the two simplest ones: rotation around its axis and revolution around the Sun, which is the Earth's orbit. However, there are also so-called millennial motions that over thousands of years modify the Earth's orientation in space. One of these is the precession motion. The Earth's axis of rotation, while maintaining the same tilt relative to the ecliptic, the plane on which the Earth's orbit lies, does not always point in the same direction. Like a spinning top that cannot stay upright and starts to wobble slowly, describing an inverted cone with its axis. So, the Earth's axis, over a cycle of almost 26,000 years, 25,770 to be precise, traces a circle in the sky with a radius equal to the angle of the axis's tilt, which is 23.5 degrees. This circle moves through the circumpolar constellations at an apparent speed of 1 degree every 72 years, gradually bringing different stars closer to the pole. Therefore, it is purely by chance that in this historical period, the star Alpha Ursae Minoris is found prospectively very close to the celestial pole. This astronomical curiosity is known in astronomy as the precession of the equinoxes, allows us to draw a parallel between what has been happening in the sky and what has been occurring on Earth over the last 26,000 years, and to relate the succession of different pole stars to human events. In 1800, during the height of the Industrial Revolution, Alpha Ursae Minoris, better known as Polaris, was already very close to the celestial North Pole, about 1 degree away. In 1610, when Galileo was revolutionizing astronomy and had just discovered the 4 major moons of Jupiter, Polaris was about 2 degrees from the celestial North Pole. In 1492, when Christopher Columbus undoubtedly used it to chart his course for the discovery of America, it was only 3 degrees away. On the night before the Battle of Hastings on October 14, 1066, the battle that awarded the throne of England to William the Conqueror against King Harold's Saxons, Polaris indicated the north from a distance of just over 5 degrees. In 800, when Charlemagne was crowned Emperor of the Holy Roman Empire on Christmas Day, Polaris was about 7 degrees from the celestial North Pole. Although it wasn't the almost perfect pole star we know today, it was still an important reference point. In 471, while the Western Roman Empire was collapsing, Polaris was about 8.5 degrees from the pole. Not very close, but no other star had yet challenged its dominance. At the year 0, the period of Jesus' birth according to the Gregorian calendar, Polaris was about 11 degrees from the pole and had been replaced in its function by the star Kochab, Beta Ursae Minoris, which at the time was 8.5 degrees from the pole. At the founding of Rome in 753 BC, Polaris was about 16 degrees away from the celestial North Pole, while Kochab held the title of the North Star, being only 6.5 degrees away. During the construction of the Great Pyramids of Giza around 4600 BC, Alpha Ursae Minoris was significantly far from the north, at a distance of 25 degrees. The pole star of the time, which the Egyptians used to align the pyramids, was Thuban, the alpha star of Draco, located about 2 degrees from the celestial North Pole. At the end of the last glaciation, around 12,000 years ago, the great fauna of the Upper Paleolithic began to disappear. Mammoths went extinct while Polaris was almost at its maximum distance from the pole, 46 degrees. No other major star was within 12 degrees of the celestial north. Around 15,500 BC, when the Cro-Magnons were painting the extraordinary animal figures on the walls of the Lascaux cave, the pole star was Vega, located about 9 degrees from the celestial pole. During the first migrations to North America around 20,000 years ago, the pole star was Aldramine, the alpha star of Cepheus, which was about 3.5 degrees from the celestial North Pole. Polaris was more than 30 degrees away. When the last Neanderthal became extinct around 24,000 years ago, the pole star was Alrae Gamma Cephei, a little more than 2 degrees from the pole, while Polaris was 11 degrees away. And finally, 25,770 years ago, at the start of this top-like spin, Polaris was almost exactly where we see it today. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. Looking to the future, Polaris has not yet reached its closest approach to the celestial North Pole. Currently, it is less than 40 arcminutes away, but in February 2102, it will reach up to 27.6 arcminutes. The effect of this small distance is evident in those striking long-exposure photos of the night sky, showing the trail produced by stars as their position changes due to Earth's rotation. The trails get shorter as the star's declination increases, but even the northernmost of all, Polaris, produces its own trail, tracing a small circle instead of appearing as a stationary point of light. For a few more centuries, the relentless precession of Earth's axis will slowly cause Polaris to recede, while Gamma Cephei will gradually take its place starting from the year 3000. Polaris will return to mark the northernmost point in 27,756, getting as close as less than 2 arcminutes from the pole. But Alpha Ursae Minoris is a star, not just an indicator. In the last century, technological advancements have made Polaris less important as a direct means of navigation. However, in the same period, its significance as an astronomical object has grown immensely. Starting from the early observation campaigns of the 19th century, astronomers have accumulated an enormous amount of photometric and spectroscopic measurements of this star. The knowledge gained from this vast amount of data is, surprisingly, somewhat disappointing. The reason, if we can call it that, is partly due to the non-perfect overlap of measurements caused by changes in technology and observation methods over the years, the variability of observational conditions, and, not least, human errors. But largely, it is due to Polaris itself, which is not only the closest and brightest, but also, as we will see, the most enigmatic of the Cepheid variables. But how close? To determine Polaris's distance from the Sun, astronomers have used the technique of parallax, the standard method for calculating distances to nearby stars. It's a fairly simple and intuitive technique that you can all try right now by extending an arm with a finger in front of your eyes and alternately closing one eye and then the other. Doing so will make your finger appear to shift relative to the background, and the closer it is to your eyes, the more it seems to move. This might seem like a trivial detail, but knowing the distance to Polaris A is crucial. As we mentioned earlier, Polaris is a Cepheid variable, the closest of its kind to Earth. Cepheids are variable stars used as cosmic yardsticks to calculate distances to far-off objects like star clusters or galaxies. Their brightness changes follow a well-defined period. The brighter they are, the longer their cycle. By measuring the period, we can determine the intrinsic brightness, and by comparing it with the apparent brightness, calculate the actual distance. However, problems do arise. For various reasons, the error in determining distances based on Cepheids is estimated to be between 7% and 20%, an approximation that might have been acceptable a century ago, but in our times it is quite unsatisfactory. The funny thing is, one of Polaris's historical features is also tied to the birth of modern photometry. But to understand how, I must first bore you with a brief overview of the meaning of magnitude. The concept of apparent magnitude dates back to a text by Hipparchus, later lost but passed down to us by Ptolemy in his Alchemist, where almost all stars visible to the naked eye were grouped into 6 orders of magnitude, from first to sixth, based on the simple impression of the observer's eye, which judged to construct a regular scale according to an arithmetic progression of intensity of sensation. This division, despite its initial imperfection, has remained foundational to the concepts of modern photometry, based on an intuition by John Herschel, who in 1831 was the first to understand that the brightness ratio between stars separated by one magnitude class is a constant, approximately 2.5. This concept was later formalized mathematically in 1856 by a young assistant at the Radcliffe Observatory in Oxford, Norman Pogson, who precisely defined the scale by setting a difference of 5 magnitudes between the first and sixth class of magnitude, as equivalent to a brightness ratio of 100. The fifth root of 100, equal to 2.512 magnitudes, is the origin of the approximate value given earlier. However, it still needed a reference point, essentially the 0 point of the magnitude scale. And the origin of the scale was set by assigning Polaris a magnitude of plus 2.12, a choice that was entirely out of place, considering it happened in the same years when there were already rumors about the star's variability. In short, the star was taken as the immutable cornerstone of the magnitude scale, even though its own brightness varied over time by as much as 30%, oscillating between 1.8 and 2.1 magnitudes with a period of almost 4 days. A funny fact to think about today, but at the time, very concerning for many astronomers. As if that wasn't enough, the situation was further complicated by another oddity, highlighted for the first time in 2004 by American astronomer Edward Guinan. He proposed that the average brightness of Polaris has been steadily increasing, going from magnitude plus 2.12 to plus 1.98 over the last century. William Herschel estimated it at around magnitude plus 2.4 in his time, and that the star has gained at least a full magnitude over the past 2 millennia. In other words, a real mess, because these peculiarities made it extremely difficult to determine the star's exact distance. That was until the early 1990s, when the European Space Agency's astrometric satellite Hipparcos measured Polaris's parallax angle at 7.56 milliarcseconds, corresponding to a distance of about 430 light-years. This value, confirmed substantially by other methods, remained until recent times. That is, until a team of Canadian, Ukrainian, and Belgian researchers used a 6-meter diameter Russian-made telescope to calculate a more accurate distance. By measuring the ratios between spectral lines throughout the entire pulsation cycle and deriving absolute magnitude and effective temperature values for the various phases of the cycle, they found a value of about 323 light-years. Could Hipparcos have been wrong? Yes, it's possible. There have been other cases of dubious parallax calculated by the astrometric satellite for Cepheids and binary systems. Polaris, moreover, embodies both risks, as it is not only a Cepheid, but, as we will see, part of a system that is more just binary. All resolved? Not at all. In 2020, there was yet another twist. The Gaia satellite, which has been in orbit since 2013 to measure stars up to 26,000 light-years away, detected a parallax for Polaris of 7.2869 MAS, corresponding to a distance of 447.6 light-years, almost identical to what Hipparcos calculated in 2007. Did this identity in the two measurements put an end to the 3-decade-long debate? I wouldn't bet a nickel on it. Not one, but 3 North Stars. That's right, in reality, the Polaris we are accustomed to seeing every night at the center of the sky is just the brightest component of a triple star system, consisting of a yellow supergiant, Polaris AA, the North Star proper, and 2 white-yellow dwarf companions, Polaris B and Polaris AB. Due to its massive size, Polaris is destined to exit the main sequence long before our Sun. As being 70 million years old, it has already lived 2/3 of its life. Polaris B, a tiny star with a magnitude of plus 8.7, was discovered back in 1780 by William Herschel, although he didn't realize it was a physical companion. Located 18.2 arcseconds from the main component, Polaris B is a main sequence star, slightly more luminous and massive than the Sun. The radial velocity, proper motion, and X-ray observations conducted with the Chandra satellite demonstrate that Polaris B is gravitationally bound to Polaris, orbiting it with a very long period, probably between 50,000 and 100,000 years. No wonder Herschel couldn't notice the movement. The distance separating it from the supergiant is estimated at 2,400 astronomical units, assuming the parallax measured by Hipparcos and Gaia is accurate. Since the early 20th century, it was known that there had to be at least one other star in the system, even if invisible to telescopes. It was discovered that the Cepheid variable's radial velocity fluctuated as if there were a significant mass orbiting it at a much smaller distance than Polaris b. The orbital period of this phantom companion was calculated to be around 30 years, but no one managed to see it, at least until 2005, when Hubble's high-resolution capabilities allowed astronomers to identify, in images from August 2, 2005, and again from August 13, 2006, the unequivocal presence of a star with a magnitude of plus 9.2 named Polaris AB and an angular distance of just 0.17 arcseconds. This distance corresponds to a real separation of just 19 astronomical units. Practically, the two stars are currently as far apart as Uranus is from the Sun. By applying the three-body problem to the Polaris system, it was also possible to determine that the primary star has a mass 5.4 times that of the Sun, while the masses of the two companions are just slightly more. Regarding the diameter, only recently have observations been able to overcome all uncertainties. In 2006, a study conducted by astronomers at the Paris Observatory used the Chera array, an interferometer that combines images from 6 different telescopes, achieving the same resolution as a single telescope with a mirror hundreds of meters wide, although with significant limitations in brightness. With this technique, it was possible to observe the star's disk and measure its angular diameter, which was found to be 3.123 milliarcseconds, a value that, at the estimated distance of Polaris by Gaia, corresponds to 46 times the Sun's diameter, or about 65 million kilometers or 40 million miles. However, something seemed off in the interferometric data. The placement of the measured points did not match the models in some parts of the curve, suggesting an interference with the accurate detection of the star's disk. After ruling out the influence of the cyclical pulsation or the binary companion, researchers concluded that the best explanation for their data was the presence of a circumstellar envelope around Polaris, with a diameter of 7.6 milliarcseconds, about 2.4 times the real diameter of the star. This envelope of gas could be explained only by the accumulation of material expelled by Polaris during its pulsations. Alright folks, there are 1,000 more things to say about this extraordinary object, so close to our history and culture, yet so distant and complex. For now, we must be content, hoping that soon more news and discoveries will compel us to talk about Polaris again, the star that, over time, unites the destinies and memories of us today and those who came before us on this planet.